Okay, for topic 4, we are finally going to talk about reference angles. So at the very beginning of this video, we had this obtuse angle and we had these ratios based on a point on the terminal side. And it was kind of like, where did these ratios come from? Well, they technically came from this idea of a reference angle, but we hadn't really talked about reference angles yet. So what we're going to learn now is going to make what we learned at the beginning of this worksheet true. Okay, so let's talk about what a reference angle is. So let theta denote an angle that lies in a quadrant. It doesn't matter which quadrant. The positive acute angle formed by the terminal side of theta and the x-axis is called the reference angle for theta. We use the variable alpha to represent the reference angle, okay? So no matter what quadrant theta lives in or what quadrant the terminal side of theta lives in, you can always draw an angle from the terminal side to the x-axis, and that is always going to be a positive acute angle, okay? And what's really cool about this is if we can understand this reference angle, it's kind of similar to the idea of coterminal angles. But if we can understand this idea of a reference angle, if we have some wacky angle and we're like, man, this is crazy, we can find a reference angle that is always positive and always acute. We can figure out what the trig function would be according to that reference angle. We just have to play around with signs, which we can now do because we understand how sines and the trigonometric functions work. Okay, so let's look at some examples of reference angles. Okay, so for this first drawing here, we have an obtuse angle. The terminal side lives in quadrant 2. So you can see, let me draw in different colors. Okay, so you can see we have theta, okay? If you look at this space between the terminal side of theta and the x-axis, this is what we would call alpha, our reference angle, okay? Looking at, and so basically you're wondering, kind of the way this would work is how much further would I need to go to get to the x-axis, or how much too far, how far past the x-axis did I go? That's kind of what's going to end up happening. So in this case here, this first drawing, it's kind of like, okay, the reference angle represents how much further we would need to go to get to the x-axis, okay? If we look at the second drawing, we have our very obvious theta, okay? And this little space, so we went past the x-axis. You can see that this angle is drawn in such a way that we have a rotation or a revolution that goes past pi and a little bit further. So we're interested in this space right here. So we went past the x-axis, but how far? So if we can figure out how much further past the x-axis we went, that becomes our reference angle, okay? Looking at this third drawing, we have a terminal side that's all the way in quadrant 4. Okay, so when we go to quadrant 4, we haven't quite made it back to the x-axis. So in this case, we're like, okay, how much further do I need to go to get to the x-axis? And that's what this right here is. That's what alpha would be. And then for this last example, we have a negative angle. You can see by the direction of theta, we went in the clockwise direction, so that tells us that theta is negative, okay? And basically we're saying, okay, we didn't quite make it to the x-axis. We didn't quite make a full revolution. So this space between the terminal side of theta and the x-axis, that is alpha, okay? So again, alpha is going to be the reference angle for theta, and it is a positive acute angle formed by the terminal side of theta and the x-axis, okay? So how much further to get to the x-axis, or how much further past the x-axis did we go, okay? Or how far past the x-axis did we go, okay? And this can be really useful for us, okay? So let's look at a couple of examples where all we do is find the reference angle. So example 7 says, good grief, I found another typo. I'm really sorry. This should say, find a reference angle for each of the following. Okay, so let's kind of draw these angles and figure out how much further we need to go to get to the x-axis, or how far past the x-axis did we go. Okay, so we have positive 150 degrees. So we know we have our vertex at the origin. We have our initial side on the positive x-axis, and we're going to sweep open, okay, in the clock or in the counterclockwise direction because this is positive. Now, 150 degrees is somewhere between 90 degrees and 180. So we know that 180 degrees is here. We know that 90 degrees is here. So we know 150 degrees is somewhere between 90 and 180. Well, it just so happens that 150 is 60 more than 90. So we would be like right here. Okay? So this right here is theta, which is 150 degrees. So let's change colors to make it really obvious. So in this case, we didn't quite make it to the x-axis. So if we look at this right here, this is alpha. And basically alpha represents how much further we would need to go to get to the x-axis. So the x-axis in this case is 180 degrees. We want to subtract our theta, which is 150 degrees. So that tells me that alpha is 30 degrees. So alpha is 30 degrees and is the reference angle for theta. Okay? Now, anytime you're dealing with degrees, it's always going to be easier to work with than radians. However, we tend to deal with radians much, much more. So embrace radians and embrace the fractions. Okay? So we have in this case negative 5 pi over 6 radians. So this is a negative angle, which means from the initial side, we're going to sweep open in the clockwise direction. Okay, so let's start drawing this and see what we get. Okay, so we have our vertex at the origin, our initial side on the positive x-axis, and we have to find a way to draw 5 or negative 5 pi over 6. So basically what we want to do is we need to know that negative pi is over here. Okay, if we can split the region from 0 radians to negative pi radians into 6 pieces, we can count off 5 of those. So let's say this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So if I sweep open in the counterclockwise direction, I'm going to go 1, 2, 3, 4, 5 pi over 6 radians. So we have theta is negative 5 pi over 6 radians. Well, the question here is how much further would I need to go to get to the x-axis? So here's my angle. How much further would I need to go ahead and make it to the x-axis? So we're interested in this right here. Now remember, reference angles are always acute and they're always positive, okay? So what would this positive angle be that would take me from 5 pi over 6 to basically negative pi? So we want to figure out what pi minus 5 pi over 6 would be. Okay, so think of that pi as pi over 1. Okay, we need an LCD. So what would I multiply the 1 by to get 6? Well, I'd have to multiply it by 6. And if I multiply the bottom by 6, I have to multiply the top by 6. So this gives me 6 pi over 6 minus 5 pi over 6. So how much further would I need to go to get to the x-axis? Well, pi over 6. Okay, so we would say that alpha in this case is pi over 6. Remember, reference angles are always positive regardless of what theta is. Even if theta is negative, your reference angle is positive. And this is the reference angle for theta. Okay? So there you have it. So you're going to be playing around with radians or degrees, and it's just how much further do I need to go to get to the x-axis, or how far past the x-axis did I go? Okay? Now we have a theorem. We love a good theorem in math, don't we? And basically the theorem is for reference angles. It says if theta is an angle that lies in a quadrant and alpha is its reference angle, then the whatever the trig function is, the trig function of theta is going to equal plus or minus the trig function of alpha. That plus or minus really matters because we now know that depending on what trig function you have, you're going to be either positive or negative depending on which quadrant you're in. So when you're dealing with reference angles, we know that reference angles are positive and they're acute, okay? And the reason we like these reference angles is because we know a lot about acute angles. We've done a lot. We know a lot about 30 degrees, 45 degrees, 60 degrees. We know a lot about acute angles. So if we can find a positive acute angle, we know a lot about that. And we can relate that back to theta. However, we always have to be mindful of which quadrant theta lives in. Okay, so if theta lives in a quadrant where it's negative, regardless of the fact that alpha is positive, we always have to make sure that theta remains the same sign. Okay, so we'll play around with this in just a minute. Hopefully, if it doesn't quite make sense now, it will in just a moment. Okay, so for example 8, it says find the exact value of the following trigonometric functions using reference angles. So remember, Sine of theta is going to equal sine of alpha, its reference angle. We just have to be mindful of the quadrant that sine lives in, or whatever the trig function is, okay? So in this case, we have sine of 150. We already kind of know what 150 looks like. We drew it a minute ago, okay? So we have our vertex at the origin. We have our initial side as the positive x-axis. We know that we need to be 60 degrees more than 90 because 90 plus 60 is 150. So that's going to put us about here, okay? So this right here is theta, which is 150. So here's the thing. We do a lot in quadrant one. We know what all the trig functions are of 30 degrees, 45 degrees, 60 degrees. So a lot of times if we can relate something back to quadrant one, those positive acute angles, we can make our life easier. It's kind of hard to memorize all of these different possibilities for these trig functions. Sine of 150 degrees, who knows, right? So let's see if we can find a reference angle, okay? So remember, the reference angle is the positive acute angle that would be formed by going from theta, the terminal side of theta, to your x-axis. So this right here is alpha, okay? Now alpha is going to be the distance between our terminal side and the x-axis. So we know if we get to the x-axis, we've gone 180 degrees. Okay, so we need to know the difference between 180 degrees and 150 degrees. That tells me that alpha is 30 degrees. So over here, we can say that sine of 150 degrees is equal to plus or minus sine of 30 degrees. And that plus or minus all depends on where the terminal side of this angle lives and what the function is in that particular quadrant. So in this case, theta lives in Q2, okay, quadrant 2. And in quadrant 2, sine is positive. So in Q2, sine is greater than 0, so sine is positive. Therefore, we can go ahead and say that sine of 150 degrees is equal to positive sine of 30 degrees, since we know the terminal side is in quadrant 2 and sine is positive in quadrant 2, okay? So we go back to our 7.3 notes, okay? And in our 7.3 notes, we have that table that I said, do your best to kind of commit this to memory. So we need to know what sine of 30 degrees is. Well, from that table, we see that sine of 30 degrees is 1/2, and it's going to stay positive. So positive 1/2. So sine of 150 degrees is equal to plus or minus sine of its reference angle, which is 30 degrees. And in this case, positive since sine is positive in quadrant 2. Okay, now let's look at cosine of 600 degrees. Now, right off the bat, we know that 600 is more than one full revolution. Okay, so this is way more than one full revolution. So this is going to equal, so cosine of 600 degrees is going to equal cosine of 600 minus 360 degrees. We can go ahead and take off one full revolution, okay? So that tells me that cosine of 600 degrees is equal to cosine of 240 degrees. Now, 240 is a little easier for us to draw. So remember, 600 degrees and 240 degrees have the same terminal side, meaning they're coterminal, okay? So 240 degrees is more than 180, but less than 270. So we know 180 is right here. We know 270 is down here. Okay, so we're going to be 30 degrees less than 270 and 60 degrees more than 240 or 180. Okay, so if we were to draw this angle, we would look like this. Okay, so this is theta, which is 240 degrees. So our question is, how far past the x-axis did we go? I've kind of already told you, but let's play around. Okay. We want to know what this angle is. So how far past the x-axis did we end up going? Well, we have 240 degrees. We know the x-axis in this case is at 180 degrees. Well, the difference between 240 and 180 is 60 degrees. Okay, so what we have now is that cosine of 240 degrees equals plus or minus cosine of 60 degrees, where this is alpha, the reference angle for theta. So let's figure out what quadrant our terminal side of theta lives in. So the terminal side of our theta lives in quadrant 3, okay? So we know that theta lives in quadrant 3, and in quadrant 3, cosine is negative. So, and cosine is negative in quadrant 3. So over here, we can say that cosine of 240 degrees is equal to negative cosine of alpha, which is 60 degrees. Okay, so again, you go back to your notes from section 7.3. We have that table that has all of the trigonometric functions for 30 degrees, 45 degrees, and 60 degrees. And we can see that cosine of 60 degrees is 1/2. But because cosine lives in quadrant 3 and is negative in quadrant 3, or because cosine lives in quadrant 3, because theta lives in quadrant 3 and cosine is negative in quadrant 3, we need to say that this is negative 1/2. Okay, so kind of similar to the idea of coterminal angles. Coterminal angles are going to be the same for these trig functions. Reference angles are going to be the same as theta, but you have to be mindful of the sign, okay? So a trig function of theta is always equal to plus or minus the trig function of alpha, the reference angle, and you just have to see where theta lives to determine the sign, okay? So I think I'm going to do actually 2 videos here. Yeah, we've got 2 more big examples, so I think I'm going to stop this video here. So we have topic 4 part 1, and then I'll do topic 4 part 2 as a separate video, okay?